We read here that a projectile is fired from a tank with an initial speed of 400 meters per second, and we're looking for two angles of elevation that can be used to hit a target 3,000 meters away. Let's see if we can visualize the situation. Now, I don't think that the author wanted us to try to guess how tall a tank is. So what I'm going to do is I'm going to assume that the tank is being fired with its cannon from a hole in the ground. Anyway, we're shooting from a height of 0. We want to hit a target that's 3,000 meters away. And the idea that there are two angles of elevation that can make that happen, I'm thinking there's one that's probably like lobbing it over there, and then one that's kind of like shooting across the ground. In any case, we're looking for an angle of elevation alpha, and hopefully our work is going to net us two solutions. We're talking about projectile motion, and so x is going to equal v naught times the cosine of alpha t, and y is going to equal negative 1/2 gt squared plus v naught times the sine of alpha t plus h naught, but I just said that by assumption we're going to go ahead and say that the initial height is 0. Otherwise it's a free-for-all. Throw in whatever number you want, and I have a feeling that's not what the author intended. Because we have here 400 meters per second and 3,000 meters, we know that we're in the metric system. Therefore, gravity is given to be 9.8 meters per second squared. Now, there's something subtly hidden in the picture that I've drawn, and it's that when the projectile hits its target, it's at a height of 0. So this point here that I've indicated on the ground is actually at 3,000, 0. In other words, when x is equal to 3,000, y is equal to 0. And that's going to be very useful for these parametric equations that we have. Let's set up what we can. X is equal to 400 times, and I wrote 4,000, times the cosine of alpha t. Y is equal to negative 4.9 t squared plus 400 times, and there it is, 4,000 again, 400 times the sine of alpha t. We have here quite a few variables, right? We've got x, alpha, t, and y. We're going to use the idea here that when x is 3,000, y is 0, but folks, that's all for one particular value of t. And so if we set up an equation using the fact that x is 3,000, we can say that 3,000 is equal to 400 times the cosine of alpha t. Whatever that value of t is, it's the same in the other equation. Notice that we're asked for the angles of elevation, and so we're asked for alpha. I'd like an equation that contains alpha, and so I'm going to solve this equation for t. We'll get t is equal to, dividing out by 100, 30 over 4, 7.5 divided by the cosine of alpha is going to be t. Substituting that t in the other equation, at the time when it's that t, we have that y is 0. We're going to get 0 is equal to negative 4.9 times the quantity of 7.5 divided by the cosine of alpha squared plus 400 times the sine of alpha times 7.5 divided by the cosine of alpha. This is the equation that we're going to work with. It has only one variable, alpha, but it has a couple of trig functions, right? We have a cosine squared in a denominator. I'm thinking that's like secant squared. And then we have sine of alpha in a numerator, cosine of alpha in a denominator. I'm thinking that's like tangent alpha. So 0 is equal to negative 4.9 times 7.5 squared secant squared of alpha plus 7.5 times 400, that's going to be our 3,000 times the tangent of alpha. Now we have a choice to make with the numerical coefficient here, negative 4.9 times 7.5 squared. I'm just going to go ahead and use the calculator value of that. 0 is equal to negative 275.625. But then we have another choice to make here. We have a secant squared in our equation, and we have a tangent in our equation of alpha, right? We can replace secant squared of alpha using something that has a tangent squared of alpha, and then we'll have only one trig function in our equation. So 0 is equal to negative 275.625 times 1 plus the tangent squared of alpha plus 3000 times the tangent of alpha. Manipulating this equation just a little bit is going to give us 275.625 times the tangent squared of alpha minus 3000 times the tangent of alpha plus 275.625 is equal to 0. You may be wondering why I'm carrying out so many decimal places, 0.625. Well, number one, that is the full decimal value of the number that we got. It terminates. And number two, I don't want to be off even by a little bit. I don't like to round off in the middle of a problem because it leads to round off error. And I'll tell you, the first time I did this problem, I made a mistake, and I'll share with you what it was later, and or at the before the video is over, and you'll see what a little mistake led to. In any case, now what we have is an equation that is quadratic in tangent of alpha. And so using the quadratic formula, we can say that the tangent of alpha is equal to 3000 plus or minus the square root of 3000 squared, I guess that would be negative 3000 squared, minus 4 times 275.625 squared, all divided by 2 times 275.625. Yeah, I know these numbers are lousy, but it doesn't matter. We're putting it all into a calculator anyway. And in fact, when I do, I can use the inverse tangent function. I'll spare you all that, and we get that alpha is approximately 84.7 degrees or 5.3 degrees. That answers the question. Remember, we were looking for two angles of elevation that can hit the target 3,000 meters away. Let's see graphs of what we just found. I used GeoGebra's graphing calculator. This is their two-dimensional graphing calculator. You can find it maybe on my website. You can Google it too. In any case, here I have the parametric equations, and I enter them as ordered pairs, just like I would using the 3D graphing calculator for a parametric curve. And for the first curve, the green one, I've got the angle 84.7 degrees. And we can see that launched from the origin, we're going to hit a height of a little over 8,000 meters, and then we're going to crash down right here at 3,000 meters and have a successful target hunting, whatever it is that we're shooting at. For the red function, I have the 5.3 degree angle, and we can see that that's really low across the ground, but because of its initial velocity or whatever's going on, it's going to also hit the ground 3,000 meters away. So this is visual verification that what we just did worked. Now, when I did this once, I made a mistake. It was a while back, and I don't remember exactly what the mistake was. I think it was somewhere around when I was dividing 3,000 by 400 or something. Anyway, as a result of the mistake that I made, instead of an angle of 84.7 like it's supposed to be, I found an angle of 81.1 degrees. Now, that's pretty darn close. I mean, we're talking 3.6 degrees off, right? But with the initial velocity of 400 meters per second, when my angle was 3.6 degrees off, I didn't hit the ground until 5,000 meters. So just a little bit off on the angle, and now I've missed my target by almost double, right? I'm almost twice as far as I was supposed to be. So for these reasons, folks, I really, really recommend making sure that we're accurate throughout the work that we're doing. Of course, the homework you're doing and the tests you're taking are not as high stakes as whatever this situation is, hitting a target 3,000 meters away. But it doesn't matter, right? I want to instill in you the desire to be accurate in your work.